Good evening and welcome to this INFOSYS-ICTS Chandrasekhar lecture series with Juan Maldacena as the speaker. So before the main show, there'll be a small commercial, so please bear with me. So welcome to ICTS for those of you who are here for the first time. Just give you a very quick overview. I won't stand between you and Juan for long. ICTS, this is how it was as a gleam in someone's imagination. Primarily Spencer's, but this was how it was a few years, 2012 or so, when the architects came up with this plan, and now finally in 2017, all the construction is over, and you see the campus, and these are just, you should go and see the library if you haven't. It's a nice design. It's one of the innovative sort of buildings on campus. And of course, we have a data center, guest house. So all the infrastructure is up and running. And of course, we've been holding programs over here, meetings, programs, and our regular activities for the last 3 years or so. But what I really wanted to say was about ICTS and its mandate, what the institution is really about. It is about putting together 3 different streams in a very tightly woven way. There's our own in-house research, and I'll say a little bit about that. But we have programs and programs, discussion meetings, workshops over varying lengths of time, 2 weeks like the particular program we are having right now, but some extending for several months, like the one on soft matter and entropy and so on from August to November. So programs of varying duration, and I'll say some more about that. And also outreach in terms of engaging with society. And these are, they're not 3 distinct components. They're sort of tied together. And we have, for instance, we have one giving a public lecture on Friday. So very often our programs and our outreach are woven. We often have many speakers from among our program participants. We have the programs are also in many ways tied up with our research, and we have an active string theory group here, which are the co-organizers of this particular program. And similarly, our researchers take a active role in outreach. So all these things are sort of tied together. In many ways, it's modeled after institutions like the KITP or the Newton Institute, IAS Princeton, etc., but with innovations to the Indian context, which I think are quite unique and therefore I think hold a lot of possibility for Indian science and in many ways even internationally. I'll just say a little bit about each of these 3 prongs of our mandate. Our research faculty are a very youthful faculty. They work in a variety of areas in theoretical physics, mathematics, quantitative biology, and going into the future in theoretical computer science and so on. At the moment, the really active areas are in astrophysical relativity, where we have a group working on gravitational waves, and in string theory, of course, in statistical mechanics, condensed matter physics, biophysics, and soft matter. A fluid dynamics group, which works on both fundamental aspects in turbulence, but also an exciting initiative to understand the Indian monsoon, and a mathematics group, which is growing right now in many different dimensions. So this is just some good press we got for our LIGO group, which played an active role in the analysis of the LIGO data. So that's normally not a journal in which you see physicists, but anyhow, it was nice to be there. The ICTS programs are on a very, so what are the programs about? They are not just meetings, but we try to be specific about trying to bring together new initiatives or thrusts into the country and get build communities of researchers in areas, incubate for them to come together and brainstorm and incubate new ideas, and even chart out new directions. And I just listed a few programs over here, things in which ICTS played a role in catalyzing a community of people in areas which weren't so well represented in India. For instance, laser plasma acceleration is a potentially innovative scientific development which can drive a new generation of particle physics accelerators, but you need to bring together laser physicists, plasma physicists, high energy physicists, and that's what our program here made a beginning in doing. But more generally, we hope to connect scientists, academia, and engineering, and industry, and so on. And we had programs in machine learning and statistical physics, which brought, again, people of very diverse disciplines together. In terms of numbers, we've had about 127 programs since inception and about 54 discussion meetings, including several of these named lecture series, the Chandrasekhar in physical sciences, Ramanujan in maths, and Turing in computer science. A large number of participants, a significant fraction from outside. And all the talks in these meetings have been archived and are available publicly on our YouTube channel, which is ICTS Talks. So if you just go to the internet, to YouTube, and you can download all the talks. We live stream most of our public events, and for instance, today's lecture. We have a great demand from the scientific community, which is why 2018 is filled. Large part of 2019 slots are also filled. So there's clearly a demand for activities here. Again, a sampling of various programs we've had, ranging from hyperbolic geometry, cosmology, string theory, strongly correlated electrons, but also in biology and astrophysics, and even going to economics. This was a particularly interesting one, which had an economist, ecologist, and probabilist organizing this. And finally, outreach. We've had various public lectures. Juan gave a public lecture long ago in Bombay. I don't know if you remember, but when ICTS didn't have this campus, but it's great to have him back now on campus giving public lecture again. All these lectures, as I said, are on YouTube, and with over 1.3 million views, and the number of subscribers on our YouTube channel is growing so fast that every time I give this talk, I have to keep updating it a lot. And I'm happy to say that right now we have surpassed the Institute for Advanced Studies in the number of subscribers. I think it's 13,000, and it was just happened in the last month or so. And several, of course, in social media. 100 Years of General Relativity was a special session we had during the Strings meeting, in which, again, Juan had given a talk. The Einstein lectures are a new initiative starting from then, in which we partner with small colleges, institutions around the country, and have many of our visitors or our own faculty go and give talks. We were part of the global initiative for maths outreach in the Mathematics of Planet Earth outreach, and organized a fairly successful live mathematical demo series, which has now been converted into a popular booklet as well. So in terms of outreach activities, these are very popular. But something we started in October 2016 has become, again, a sort of an institution in Bangalore. This is something modeled on something that's there, that TFR in Mumbai had started, Chai and Vai. So here, of course, Kapi, which is coffee, is more popular. So it's Copy with Curiosity is our monthly event, which we are holding at the planetarium. And it has a nice format of giving equal time for the talk as well as for question and answers. And people are now, it's being live streamed, and people are now even asking questions over the chat. And we've had a sort of a steady audience, a loyal audience now. There's one next Sunday, this coming Sunday, on, in fact, black holes and steam engines. So by Joseph Samuel from RRI. So this has been a particularly popular series. And during our 10th anniversary, we had a great public lecture by Kip Thorne out there in the foyer, which was like a rock concert with 1,200 people coming and multiple big LED screens. And we had a panel discussion with Robert Digraph and others. A lecture by Robert Digraph followed by a panel discussion, as well as a technical set of 3-day meeting, which was across a wide variety of disciplines. So that's all for the commercial, and so I'll now hand it over to Spenta to introduce the speaker for today.
Thanks. Thank you, Rajesh. So when I was asked to introduce Juan, I was wondering what is there to introduce. The speaker actually needs no introduction. But then, given the fact that there are many, many very young people here, it might just be appropriate also to introduce Juan formally. So Juan Martin Maldacena is the Carl P. Feinberg Professor in the School of Natural Sciences at the Institute for Advanced Studies in Princeton. And he's originally from Argentina, and his early education was in the University of Buenos Aires, and then at the Licenciatura in 1991 in Bariloche. And his mentor there was Gerardo Aldazabal, whom I myself knew. Postdoctoral work was at PhDs at Princeton University in 1996 with Curtis Callan, and Rajesh and Juan are basically classmates. One of them worked with Callan, the other one with Gross. Postdoctoral work was in Rutgers, and then he was a professor at Harvard for a couple of years, and then back to the Institute for Advanced Studies in 2001 till present. So he actually also is involved in many synergetic activities in the developing world. For example, he's a member of the International Advisory Board of the ICTS. He's also a member of the Scientific Council of the International Center for Theoretical Physics in Trieste, and also a member of the steering committee of the ICTP South American Center for Theoretical Physics in Sao Paulo. He also was a member of the Committee for the Mathematical Sciences in 2025. It was a study which was requested by the National Academy of Sciences of the United States. It's a fantastic document, all of you. I have read it and gained from it. I will advise a lot of the senior people sitting here to have a look at that document. So now let me come to the main part, scientific contribution of Juan Maldacena. So in 1997, as we know, Maldacena proposed and gave evidence for the ADS-CFT correspondence, in which the precise dynamics of type 2 string theories in an asymptotically ADS5 spacetime, I'm a physicist, I want to be accurate, is equivalent to n equal to 4 supersymmetric non-abelian gauge theories in 3+1 dimensions. Okay, that is all written. Now, what was the impact of this? This impact, of course, I also felt very strongly, because those of us who were students in the mid-70s, 1970s, were obsessed with trying to understand how to solve the problem of quark confinement, and later on, even in the late 80s, how to understand the conundrums actually, how to solve the conundrums presented by black holes. So you can imagine what this paper did actually to a whole generation of people. So it solved two major problems in principle right away, and that's absolutely amazing. It showed that the large n limit of n equal to 4 non-abelian gauge theories is described by Einstein's equations corresponding to type 2 string theory. There is a large, so he discovered the large n mean field of Yang-Mills theory, and that lives in one higher dimension and is governed by Einstein's equations of general relativity. I mean, that's quite incredible. What was the second point? The second point is that it implied that black holes, which are solutions of Einstein's equations, can be understood by studying strongly coupled large n gauge theories, which are unitary quantum field theories. So this means that the information puzzle has in principle a solution within the ADS-CFT correspondence. So these are the two big things that this paper actually did. And it introduced the idea that space-time itself is emergent from interactions of non-gravitational type of theories. I mean, this is quite radical. Okay, let me go on. So a large part of these past 20 years has gone into unraveling this correspondence and its implications both ways. I don't want to give these details, except that saying that ADS-CFT opened the floodgates in theoretical physics, and string theory began to have a unifying effect on all of theoretical physics. In the sense, I mean, especially string theorists earnestly started using classical gravity to understand strongly coupled many-body systems. And it's matter physics, statistical mechanics, etc. And, you know, I mean, it's just not a formalism, but some very important results have emerged of universal applicability from the ADS-CFT correspondence. And I'd like to name a few of them, and some of the originators of those ideas are also present over here for this celebration. So the first thing I would like to quote is the formula for the viscosity divided by the entropy of strongly coupled fluid. An exact formula can be derived for that from the ADS-CFT correspondence. That's an amazingly beautiful result, very significant. So you could access the idea of trying to compute transport coefficients in strongly coupled systems using the ADS-CFT correspondence. Who would have dreamt of that? Then there was this amazing formula, the Ryu-Takayanagi formula, actually, which opened another important dimension in our understanding of the importance of entanglement entropy, and entanglement per se also in the theory of quantum gravity, which I think is one of the main themes, even so succinctly summarized by Juan and Susskind in the famous equation EPR equal to ER. Then there is the holographic description of higher spin bulk theories in 3 and 4 dimensions by conformal field theories in 2 and 3 dimensions, which was done. And for example, the first hint of all these interesting dualities of Chern-Simons matter theories, which people have been discovering and working on, the first hint of that was found in Vasilyev's theory of higher spins in ADS-4. And I can go on and on. Just to make one more point, Juan also has a keen interest in cosmology and early universe physics, to which he has made basic contributions, especially in connection with the non-Gaussianity of primordial fluctuations in the inflationary universe. So in summary, I can say much more, but Juan is perhaps the brightest beacon that we have as we navigate the dark and difficult alleys of the theory of quantum gravity and cosmology. For all this amazing contribution, he has been made a member of the National Academy of Sciences of the United States. He's also a member of the World Academy of Sciences in Trieste and the many other learned societies. His awards, I don't want to list all of them, but I definitely want to mention the Denny Heinemann Prize for Mathematical Physics, the ICTP Dirac Medal, the inaugural Fundamental Physics Prize, and the Lorentz medal, which was in 2018. And I just like to close this little discourse by asking the question, why we are here at ICTS to celebrate 20 years of ADS-CFT. Now, the idea of this meeting is due to Loganagam, who is one of the organizers of this meeting. And he said in his way that we need to do something about ADS-CFT because, we are all making a living out of it. So that struck me very deeply, and I said, yes, let's do it. And I think that's why we are all here. And thank you, Loga, for this talk. So without any further ado, I'd like to invite, Rajesh to carry on the ceremony.
Thank you very much, Spencer.
Okay. Thank you. Thanks for the very kind introduction. I'm very happy to be here. I'm very happy to see this institution working so well and doing all kinds of exciting physics. And I'm very glad to be part of this very nice program. So we'll discuss the relationship between quantum mechanics and the geometry of space-time. Of course, in the ancient times, the people thought the geometry of space was Euclidean. And then people discovered that you can also have non-Euclidean geometries, for example, hyperbolic space. And then it was realized that Euclidean space plus time formed a Minkowski space, or the space-time of special relativity. And then these two together give rise to the metric of our space-time, which is described by the theory of general relativity, or sometimes called geometrodynamics, so where the dynamics is really the dynamics of geometry. Now, this theory made two very surprising or stunning predictions. And the first one is the existence of black holes, and the second, the expanding universe. Now, these predictions were so surprising that they surprised even Einstein. And that's encapsulated in this phrase that Einstein told Lemaitre, who was proposing the expanding universe. He said, "Your math is great, but your physics is dismal." And I like this phrase very much because that's sometimes what people tell us string theorists. Now, they are both surprising because they involve drastic stretchings of space and on time. And now, that's all in the classical theory. And of course, many of these predictions of the classical theory have been verified. And well, the discovery of gravity waves was one very wonderful confirmation of this theory, and the fact that geometry plays a role in describing space-time. But we also have quantum mechanics, and the question is, what's the relationship between quantum mechanics and space-time? So the general relativity is what we call a classical field theory, so it's a theory described by classical equations, and in principle we should quantize it. And because it's difficult to change the shape of space-time, in fact the whole Earth is barely changing the shape of space-time around us. For that reason, for most situations, the fluctuations of space-time geometry are very small, and we can treat them well by thinking of small quantum fluctuations around a fixed geometry. And that approximation works well in a very big range of, well, basically for all the processes in most of the processes in the observable universe. And this simple perturbative quantization has very interesting consequences that we're going to see in a second. But there is one big problem for which we need a full theory, which is the beginning of the Big Bang. So there, the simple perturbative quantization doesn't work. And the main motivation for developing a theory of quantum gravity is to explain the Big Bang. I have nothing more to say about the Big Bang, but that's our main motivation. So let's say what there are interesting predictions of this perturbative. Let's go back to this perturbative quantization, so small fluctuations around the space-time geometry. And they have some very surprising predictions again, two surprising predictions. One related to black holes, so black holes have a temperature. And the second is that the accelerating universe also has a temperature. So the temperature of a black hole, this is the formula that Hawking discovered, the formula for black hole radiation. And so this formula is saying that the radiation coming out of a black hole has a wavelength proportional to the size of the black hole. And the accelerating universe also has a temperature, and again, the temperature is related to the size of the horizon, the distance to the horizon. So it's essentially the same formula, and it's basically the same kind of effect, and we should really think of it as a unified way. And this first thing has not been seen experimentally yet, but this second effect we think is very, very relevant for us. And this is related to the theory of inflation. So inflation postulates that there was a period of expansion with almost constant acceleration. If classically it would produce a very large homogeneous universe, so it would produce this expansion gets rid of any initial inhomogeneities and produces a very flat and uniform universe. Now that's not exactly the universe we live in. So the idea is that small quantum fluctuations that are produced by these effects that we were discussing are due to the temperature in that expanding universe, give rise to very tiny fluctuations, which are the things that we see as inhomogeneities in this map of the cosmic microwave background that you probably have already seen before. So one interesting consequence of this is that quantum mechanics is actually crucial for understanding the large-scale geometry of the universe. So you can view this map as showing what the geometry of, let's say, a spatial slice of constant density looks like. And the geometry is not exactly flat. It has small fluctuations, small curvature fluctuations. And those fluctuations are due to the quantum mechanics in the early universe. Now, it's often people say and emphasize a lot that quantum gravity is relevant at short distances, and that's correct. But it's also relevant for long distances. So these quantum mechanical effects related to gravity really are important at long distances. So this is a bit like the quantum foam of the early universe, not quite as violent. It's a very tiny effect, 10 to the minus 5 effect, but we really see it in the universe, and it's very important for explaining the phenomenology of our universe. Okay, so this is a first instance, let's say, of the connection between quantum mechanics and the geometry of spacetime, and throughout the talk we'll see other connections of deep connection between the two things. So now we'll discuss more theoretical developments suggesting a stronger connection between quantum mechanics and the geometry of spacetime. So one of them is this gauge gravity duality, or gauge string duality, or sometimes called ADS-CFT or holography. Has many names. They all mean essentially the same. And it's a relationship that relates theories of quantum interacting particles. An example is quantum field theory, or could be quantum system, non-relativistic quantum system, with a theory that has a dynamical spacetime. So that might be governed by general relativity or string theory. Typically you have relationships that says that some very concrete quantum mechanical theory is equal to some very concrete string theory, completely well-defined. And then typically you have that if you take very strong coupling, so you take this theory and you take it at very strong coupling, this corresponds to this string theory in the limit that the string size is very small. And I'm not describing yet what is string theory, but all you need to know is that when the string length is very small, it reduces to Einstein gravity plus some other theories. And so here you have a concrete, very strongly coupled quantum mechanical theory, and then that's related to gravity. Okay? So you have a relationship between a quantum mechanical theory and some theory that has a geometric description. In that sense, it's a relationship between quantum mechanics and geometry. So I will discuss one example of this. So some of the examples, some of the first examples involve quantum field theories, which are a little more complicated things, but we'll start with one of the conceptually simplest examples, which is a system of harmonic oscillators. So imagine you have some harmonic oscillators, and we also have some Majorana fermions. So Majorana fermion is roughly like a fermionic harmonic oscillator. So we start with this. This is a free theory, and now we introduce some interactions. We have some interactions that relate the bosons and the fermions, and some self-interactions between the bosons. So that's roughly what the theory is. In fact, to find this gravity dual, for some technical reasons, we need to assume certain symmetries. So these are harmonic oscillators, but they are arranged into matrices, so into a matrix with n square components, so n by n matrices. And in addition, there are 9 of them, 9 of these matrices. And they interact in a particular way that respects a bunch of symmetries that I'm not going to detail. But it's nothing more than a bunch of harmonic oscillators interacting in a specific way. And all the interactions are fixed by a certain this UN symmetry that rotates this n by n matrix, and some other symmetry called supersymmetry that relates the bosons and the fermions. And this theory has an effective coupling constant, which is given by this coupling. And because there are n matrices, it's enhanced by a factor of n. And there is a characteristic energy scale, which was the frequency of these harmonic oscillators. And this is the effective coupling of this theory. And the idea is that when we are at very strong coupling, so that G was the coefficient of the quartic term, that is very large. When that is very large, and also we are at, let's say, temperatures such that the effective coupling at the temperature scale is very large, then we can find a geometry, and that geometry is a geometry which actually has 10 dimensions and is a solution of so-called 10-dimensional supergravity. And basically, it has 2 dimensions, one of which is the time direction that we already had in the quantum mechanical theory. And the other one is a radial direction, and we have a kind of black hole. So the geometry has basically the shape of a black hole, has a horizon. And we also have an 8-dimensional sphere. That the fact that we have an 8-dimensional sphere had to do with the fact that we had we had 9 matrices related by an SO9 symmetry. And the curvature radius of this solution is proportional to the effective interaction strength. So the bigger the interaction strength is, the bigger the curvature, the bigger the radius of curvature of the solution is, so the more we can trust the gravity solution. And you can then, for example, using in gravity, you have a formula that tells you what the entropy of a black hole is. This is the famous formula of Bekenstein and Hawking, which comes from the formula that Hawking derived for the temperature that we saw in the beginning. By using the laws of thermodynamics, you can also derive this formula. And using this formula, we can calculate the entropy and free energy of this black hole, and that should be equal to the entropy and free energy of this strongly coupled system of harmonic oscillators, right? So that's a strongly coupled quantum mechanical system, and you can try to calculate. And so it's difficult to do that calculation analytically in the quantum mechanical side because it's strongly coupled. We don't have good techniques to do that, but one can do a comparison with a numerical calculation. So here is the temperature in the horizontal direction. Here we plot the energy, the internal energy at a given temperature, and from this we can get all the other thermodynamic quantities. And so high temperature in this system corresponds to weak coupling, and low temperature to strong coupling. And then we have the curve that we can calculate using the Hawking-Bekenstein formula, which is this curve here, okay, the black curve, the continuous black curve. And then we have the results produced by the numerical simulations, which are these points here, okay? And you see that they don't agree, okay? But they don't agree for a good reason, because here we're at weak coupling. They are not supposed to agree at weak coupling. We are supposed to agree only at very strong coupling, and indeed, when you go to very strong coupling, if you extrapolate this curve, you see you get closer and closer, and you can match this curve to the result from gravity plus some corrections that you expect in general in gravity, and you can match all these coefficients, and you get here an agreement which is pretty good with the gravity result. Okay. Okay, I think there is some feedback. Did you hear feedback? Maybe I'm standing in the wrong position. Yeah. Okay. Now, so we can ask why here. I should stand. That's the reason. Okay, so why do we have this kind of relationships between this type of relationships we have done? So let me. It's a bridge between two regions. Yeah, built by people that. Yeah. That's right. Yeah. Mm-hmm. So a very brief history of why you expected a relationship like this. So first is that strings are observed in nature, as Penta briefly said. So there is an experimental observation, which is that strings are produced in hadron colliders, and they decay to other hadrons and so on. Hadrons are the strongly interacting particles. And so the theory we use to describe the strongly interacting particles is QCD, so quantum chromodynamics. And we think that somehow strings come from quantum chromodynamics, are described by quantum chromodynamics, but that involves strong interactions. And a simple limit to understand the emergence of strings is to take n colors instead of 3. So quantum chromodynamics has 3 different colors, but you can consider theories where you have n colors. So colors is. So in quantum chromodynamics, the basic variables are organized themselves in a matrix, 3 by 3 matrix. But then you can consider a version of the theory where you have n by n matrices. And that's what we call, the rank of the matrix is what we call colors. And we can take the large n limit. And in the large n limit, so the basic variable, which is the gluon, is a matrix with 2 indices. And you can think of it as having a color and anti-color. And in the large n limit, there is a strong interaction between a color, a gluon of a given color, and another gluon that has the corresponding anticolor. And then you start forming chains of gluons whose colors are correlated with the anticolor of the next. But in a situation like this, for example, this gluon will not interact strongly with one whose color is not correlated. And in that way, we form this kind of necklace. And the strong interaction makes sure this necklace is quite bound to the next gluon. And in the limit that we take this effective interaction strength to be large, we expect to have something that behaves like a string. And that's a qualitative explanation for the strings that we observe in nature. And closed strings would be what we normally call glue balls in QCD. Yeah, so roughly speaking, the G square n is governs the size of the string of the space where the string is living relative to the in-string units, right? So the bigger Gn is, the smaller the size of the string will be. Okay, so as I said, we had experimental evidence for these strings, and it was initially thought that these strings propagate in 4 dimensions, but it was then realized that they should move at least in 1 more dimension. So the string in 4 dimensions is not quite consistent on its own. You really need at least 1 more dimension. And unfortunately, we don't know the precise string background for large N QCD, so for the version of QCD that describes our world, at least the large N version of it. There should be some string theory. We don't know exactly what it is. But we do know it for its maximally supersymmetric cousin. So supersymmetry is some extra symmetry that the theory can have. So you change the theory, so you can solve the problem for the theory you would like. So you change the theory a little bit, and then you solve that problem. It's like this story about the spherical cow. You know, yeah. So this is a hyperbolic cow. Okay, so and this relationship was obtained the following way. So it was obtained thinking about string theory. So string theory is a theory, a simple version of string theory lives in 10 dimensions, and in those 10 dimensions you had some objects which are a bit like solitons that can have various dimensionalities, and one particular example involved solitons that have 3 spatial dimensions and 1 time direction. So they're built like a membrane and that sits in that 10-dimensional space. And Polchinski found a very precise description of these branes. So exactly when you have those branes sitting there are some excitations of these branes, and these excitations interact with each other in some way, and he gave a precise prescription for how they do that. The same branes can be viewed as objects that have some tension, and so or some energy, and then they curve the space-time around them, and they create a curved geometry, which has the geometry of a black brane. So a black brane is roughly like a black hole, but extended in space. And then one can take a low energy limit of this relationship. So one can think that these two describe basically the same physics. And that low energies, the theory that lives on these branes is this supersymmetric version of chromodynamics. And the geometry near the horizon of these black branes is 5-dimensional space, hyperbolic space, with time, sometimes called ADS space, and a phi sphere. And the idea is that the probabilities you compute in the quantum particle theory, so you have this theory of chromodynamics on the boundary, and this works in all cases. So you have that quantum mechanical system on the boundary, and you can compute probabilities there or amplitudes there, and those probabilities or amplitudes are computed by, let's say, particles that move in this higher dimensional space. So you have the probability amplitude that the particle goes from here to here is the same as similar probabilities in the quantum theory. So for example, if you calculate correlations of the energy momentum tensor on the boundary or energy correlations on the boundary, that's related to the propagation of gravity waves through the interior and properties of those gravity waves. Now, there are many examples of this, and there are many checks that are very impressive, especially at large n. There are lots of checks, but it's not proven. So these relationships are not proven, and there is no general method of going from the quantum field theory to gravity. And the precise mechanism by which the geometrical description emerges and the precise translation between the variables of one and the variables of the other has not been understood and are being investigated, and people are making progress and getting closer to finding a more precise relation between the two things. But in the meantime, there's been lots of connections between different areas of physics. We have connections between black holes and the quark-gluon plasma. So that's the thermal phase of quantum chromodynamics. And there are also relationships to non-trivial phases of quantum matter physics, where, again, you have some strong interactions, and thinking about this duality can help you get some intuition about those strongly interacting systems. Some methods of quantum information theory, quantum error corrections have been useful for understanding the relationship. And these relationships have been useful going in both ways. So they have taught us something about gravity, something about black holes, and we also have learned some things about general quantum systems. So I'll discuss one example of this way of relationship. There are many others, but I'll discuss only one. And that's a universal bound on chaos inspired by black holes. So this is a bound that's supposed to hold in any system that contains many degrees of freedom, that many-body system, quantum many-body system, and it was inspired by black holes. So I'll try to explain how one got inspired to discuss this bound, and so on. So first, let me remind you some properties about chaos. So if we have classical chaos, is the idea that you have some trajectory of some system in phase space, and you start with a nearby trajectory, you change the initial conditions a little bit, and then you evolve, and then you find, if the system is chaotic, you find that these trajectories diverge from each other. If you, for example, you change the initial velocity a little bit, then the position of the particle at some later time, so you change the initial velocity at time equal to 0. After some time, the position will have changed, and the difference in position grows exponentially with some characteristic exponent, which is called the Lyapunov exponent. And then this can be computed by, the change in the position relative to the change in the momentum, it can be viewed as in terms of a Poisson bracket. Now we could take also the square of the Poisson bracket, it's also growth. And the quantum analog of this would be to take the commutator between the operator at time equal to 0 and the operator at a later time, so that's the analog. We take the square so that the operator is positive, and then we can take, and then we calculate, let's say, if we have a thermal ensemble, we calculate the average, we can calculate the expectation value of this operator to get a number, and a useful case is to take that expectation value in a thermal ensemble. And then we define the quantum version of the Lyapunov exponent as well, in terms of the exponential growth of this quantity. The same way that classically there was a growth in the position, then quantum mechanically there is a growth in the behavior of these operators. Notice that sometimes people incorrectly say that quantum mechanics is not chaotic because the Schrödinger equation is linear, right? But chaos is not manifested in the wave function, but in the behavior of operators. And the same is true in classical mechanics. In classical mechanics, the Liouville equation is linear, but it's these operators, or if you wish, the functions in phase space that display chaos. Yes. Yeah, you could take the fourth power. Here is a square simply because so that it is positive and there are no spurious cancellations. Okay, so in general we define this, and in a large n system, typically these commutators will be suppressed by 1/n, because the idea is that you have a system with many degrees of freedom, many, let's say, qubits, and you change one of them is V. And then you wait some time, and after some time you look at you act with some operator that changes another one, different from the first one. So here V and W are two simple initially commuting observables of a large many-body system. So n is either the number of qubits or the entropy of the system, and this is just the definition of the quantum Lyapunov exponent. Of course, we are defining it as in terms of the initial increase, so the commutator starts being 0 at time equal to 0, and then it increases exponentially, and at some point it will saturate to some maximum value, which will be of order 1 if these operators are simple operators like sigma matrices, for example, acting on a given spin. So here, the Lyapunov exponent is determined in terms of this initial increase. And now we will use holography and black holes to compute it, to compute this Lyapunov exponent to see what it is. So the idea is that if you have this gauge gravity duality, if you have a black hole, it's describing everything that happens in ADS, has some translation to something that happens on the boundary. And in particular, if you have a black hole, that should correspond to a hot fluid made out of very strongly interacting particles on the boundary theory. Okay. So the chaotic system we were talking about before could be this fluid of very strongly interacting particles, and we're going to do the computation of this commutator by using the gravity description. Okay. Here this is a diagram of the space-time. So we have the time direction here, and we have the horizon. And so we're going to imagine we have two operators. One is at time, this point here is time equal to 0. This other point here is some later time. Now, when you act with the operator, you create some excitation that goes into the black hole. And similarly here, you act with the operator, you can you create an excitation. You can also evolve that one backwards in time and comes from some other excitation that comes out of the black hole and then goes into the black hole. Now here the important point is that the commutator is computed. Turns out, I'm not explaining this in detail, I'm just giving you a brief outline of how this calculation goes. The commutator will be related to the scattering amplitude of these two particles in the geometry near the horizon. And the important point here is that when you separate these two operators in time, you let time pass and you separate them by a very relatively long time, so long compared to the inverse temperature of the black hole. Then in that case, these two particles will be very close to the horizon, and very close to the horizon, the time translation at infinity acts as a boost, as a relative boost between these two particles. So when you look at this at later and later times, these two particles will have a higher and higher boost relative to each other. So they will be colliding faster, and turns out that the interaction that grows fastest with energy is the gravitational interaction, because gravitational interactions are proportional to the energy, so they grow fastest. And this interaction between these two fast particles is related to the so-called Shapiro time delay. It's an effect of general relativity. And it grows as the energy, so this amplitude grows like the energy, or the phase shift goes like the energy, and the energy grows exponentially with the time. And when you put the precise coefficient here, you find that it grows exponentially with time with an exponent, which is given by the temperature of the black hole. Okay? So that's the calculation of the exponent using the gravity theory, and it follows from geometric properties of the black hole. So from how time translations act near the horizon, they act as a boost, and that's how we got this answer. Okay, so that's what we get in gravity, and we can ask whether it could be different. So we got a definite answer. Now, the Lyapunov exponent in general systems could have different values. So you can have a weakly coupled system. The Lyapunov exponent would be very small because there are very, very few interactions there. And so we can ask whether we can change this value by making the interactions a little weaker. So we said that the very strongly interacting system is described by gravity. As we make the interactions weaker and weaker, it will be described by string theory. So we'll have to, in order to see what would happen if we made the interactions weaker, we need to include string corrections. So I won't discuss all the features of string theory. All I'm going to say is simply that when you scatter strings instead of gravitons, or you take into account that the graviton is made out of a little string, then the high energy behavior of the amplitude gets changed a little bit. So it's not like in Einstein gravity, it's just a little, it grows a little less rapidly than in Einstein gravity. And so then the Lyapunov exponent, when you feed that back into this black hole geometry, turns out that it is the maximal value that we had in the Einstein case, minus some small correction, at least when the string length is small, some small correction which goes like the string length divided by the radius of the space. So it can be a little smaller if you put in the string corrections. So it can be less, but you can ask whether it could be more. So could it be that there is some other setup where it's bigger than that value? And it turns out that if so we saw that this exponent came from a scattering amplitude in the black hole geometry, right? So then let's forget about the black hole geometry and think about scattering in flat space. So we need to understand how scattering in flat space grows with energy. Now it turns out that if you have a causal theory, the scattering with energy cannot grow faster than the energy. So if it grows faster than the energy, then you can send the signal faster than the speed of light. So by scattering, I'm not explaining exactly why, but you have to believe me, that there is a constraint just from scattering in flat space that the power has to be less than 1 to have a causal theory. So maybe this inspires you to think that maybe there is a general bound, not just simply valid for systems that have a gravity dual, but maybe for general systems. And indeed, it turns out that there is this universal bound that you can prove just. So now you forget about gauge gravity duality, you forget about everything I've said so far, and you just say, well, I have a large N quantum system, and we use only properties of unitarity and analyticity in Euclidean time and so on. So some simple properties that are true for any system. And using those properties, you can show that this Lyapunov exponent is always less than the temperature. Okay? And not only that, but well, this also shows that the black holes are saturate this bound. So they are sort of the maximally chaotic systems that you can have. Yes. Yes, yeah, so large N comes because if you don't have large N, there was this curve where the commutator starts being small and then it grows, right? If you don't have large n, then it grows pretty fast, and you cannot extract an exponent from this rise, okay? So it is involved in the very definition of the Lyapunov exponent. Otherwise, you cannot define it. Yeah. Okay, so now let's go back to quantum mechanics and the geometry. So I finished the discussion of the one example for how these two things are connected. And so now we go back to the quantum mechanics and geometry relation. And I'm going to discuss some connections between entanglement and geometry. So entanglement is a very basic quantum mechanical property. It's what distinguishes quantum mechanics from classical mechanics. And it turns out that in this duality, the entanglement pattern present in the state in the boundary theory will translate into geometric features in the interior. And so we think that then the space-time geometry is summarizing the entanglement properties of the quantum mechanical system. And so Spenta mentioned the Ryuta-Kanagi formula. And so this is a formula that, so given the boundary theory, so here the blue line corresponds to the boundary system in a situation, let's say that we have one spatial dimension. So you can think of this as a quantum mechanical system with one spatial dimension that has a gravity dual. So it has, the gravity dual has some extra direction that goes down here in this page. And in this system, you can consider either the whole system, in which case, let's say you have the vacuum, you have a pure state, which is the vacuum, or you can restrict your attention to some subregion, which is this subspace of the boundary, so a little segment. Now, if you only look at the degrees of freedom here in this segment, you will find that the state is not pure. So you'll get a non-trivial density matrix, and there will be some entropy. That density matrix will have some entropy. And the idea is that, so the Ryuta-Kanagi proposes that this entropy is calculated by looking at the minimal area surface in the bulk, so in the bulk geometry, that ends on the boundaries of this region. So here, this quantity that quantifies the amount of entanglement, which is the entropy, has a geometric meaning as the area of this minimal surface. So this formula is a generalization of the Hawking-Bekenstein formula for black holes. So the Hawking-Bekenstein formula is also a formula that tells you the entropy of the black hole in terms of an area, and this is something similar but a little more general. So another manifestation of this connection between entanglement and geometry is the following: is this interpretation of an old solution. So there is the old Schwarzschild solution, which Schwarzschild found just a year after Einstein found the equations of general relativity. He wrote down the simplest spherically symmetric solution, and that solution was very confusing in the beginning. Eventually, it was understood that that solution described actually two black holes. So it's, and in the case that the black hole is in anti-de Sitter space, so it has this diagram, and it is, so this triangular region here represents the exterior region of one of the black holes. And then there is a second black hole here, which is the exterior region corresponds to the triangle here on the left side of the diagram. So if you haven't seen these diagrams before, here the vertical direction is time, and well, the radial direction is the radius, and these 45-degree lines represent the horizon of the black hole. And what's peculiar about this is that the two black holes share an interior. So there are two black holes in two completely different spacetimes, and they share a single interior. Okay. And this is just the simplest solution of GR. So it's not something very esoteric. And the idea is that in this setup, we have two boundaries. And we said that when we have an asymptotically anti-de Sitter space, on the boundary we have the quantum system that's supposed to describe the interior. And so here we have two boundaries, so we have two quantum systems. And the idea is that this type of geometry is described by an entangled state in an entangled state in in those two systems. So we take a particular entangled state, and it's an entangled state that you form using thermal looking weights. In fact, this state is closely related to the thermal ensemble, because if you trace out the left, you get the thermal ensemble here on the right, the canonical ensemble, or the canonical density matrix. Yeah, so that's the state that we have. And so notice that it's important that it's entangled in the sense that, well, in order for this interpretation to be correct, it's important that we cannot send signals through this geometry from one side to the other. And so if this person wants to send a signal, so let's call him Romeo, he cannot send the signal to Juliet, okay? And that's consistent with the interpretation of this geometry as an entangled state. And in fact, you might wonder whether if you perturb the geometry a little bit, you might be able to, because you almost can send the signal. If you send the signal very close to the horizon here, it almost gets to the other side. So you might wonder if you just deform this geometry a little bit, can you actually send the signal? But it turns out that in this type of geometries, you can show that you can never send the signal because of some property of matter. So when you have general relativity, it should obey Einstein's equations with some matter, and that matter obeys the so-called integrated null energy condition. And this condition was proven with quite generality in flat space and in context similar to this. Well, in this black hole context, it's a similar argument. And so this is saying that these black holes are not good for science fiction. So at least the usual science fiction stories that would allow you to travel between very distant places. But they are good for science. So. Now, so the idea is we can think of these black holes in the context of this duality. So we imagine we have some strongly interacting quantum systems in the lab, right? And we form an entangled state of these quantum systems. And the idea is these quantum systems would have a gravity dual. And this gravity dual will have a horizon, so each one will have its own horizon. But the idea is that they are connected through the interior if these two were entangled. So let me try to explain what it means for them to be connected through some simple thought experiment. So let's some simple story. So it's a kind of variation of a science fiction story. So we have Romeo and Juliet. They are in two very different galaxies. Their parents don't want to meet them. Sorry, I'm not telling it properly. This is the standard Romeo and Juliet story. So we have Romeo and Juliet. Their parents don't want them to meet, so they separate them, put them one in one galaxy, they are in another galaxy. It's in the future, in the very far future. But they are very determined, and they exchange. The parents allow them to exchange messages and qubits and so on. So by exchanging qubits, they manage to build two black holes that are perfectly entangled in the particular state that we discussed, the so-called thermophile double. And then after they do that, then we have the black hole here. Romeo here is in the Milky Way galaxy. We have Juliet in the Andromeda galaxy. They're very far away, these two black holes. But through the interior, they are very close. Okay. So if Romeo is 1 meter away from this black hole and Juliet is 1 meter away from this black hole, they are millions of light years separated in the ambient space. But through the interior, they are 2 meters away. Okay. So they set up this situation, and then they jump into their respective black holes. So let's first look at the bottom. And so we have Romeo falls here, Juliet falls here, and they die. Okay. That's what people outside think. They committed suicide, right? So they say that's too bad. And that's what the narrator of the story said, okay? Now, since they arranged this very specially, what they actually feel is what the diagram up here. So they jump into the black hole, and they actually meet in the interior of the black hole, right? And they can live there for a while. Eventually, they will die when they get to the singularity. So this version of the story doesn't end well. There are some other variations where you can end it a little better. So this is this variation. So I'm going to now do another variation of this, where just to end the story a little better. And this variation involves an interesting connection between quantum teleportation and this variation involves a different approach that Romeo and Juliet could follow to meet each other. Okay, so they read this paper here, and they had exchanged all these qubits. Okay, and according to this paper says that if you are sharing a bunch of qubits that are entangled, and then you want to send Romeo, so let's say the Charlie's qubit is actually all of Romeo, then you can do here a measurement on both the things you want to send and these entangled pairs that you're sharing. And then if you do that measurement and you only send classical information, then you can recover the message, okay? So then they read this, and then they said, well, let's just send one of them. So let's say Romeo wants to go this way. But he was a little uncomfortable about this measurement thing, because in teleportation, you take this message and you take the qubits, and then you apply a unitary transformation that mixes them up, okay? And then you do a measurement. And this idea of taking a unitary transformation that mixes you up with a bunch of qubits doesn't look very pleasant, okay? And so they were a bit nervous about this procedure. So the question is whether you would agree to be teleported this way, okay? So let's say someone invents a machine that would do this, so would you agree? I mean, they guarantee that you will be recovered here with all your memories intact and so on, but you are worried that you will experience something bad here. So now they actually read this other paper, which said that if you that actually, if these entangled systems are not anything, but they are actually systems that have this black hole interpretation, then this whole procedure has a very interesting way of proceeding, which is that first, the entangled state has interpretation of a black hole with this common interior and so on. So this connected geometry, which you can think of it as a wormhole. And then, so Romeo could jump in here and then arrange for a measurement being done here at the left. And then the information of the measurement is sent classically to the other black hole. And then here you can modify the evolution of this black hole. You can introduce, you can basically extract some energy from the black hole. So by doing the measurement here and the fact that this feels that there are correlations between, and there's entanglement between the two sides, you can effectively extract energy from this black hole and send a negative energy pulse. And so then Romeo was going in here. This negative energy pulse produces a time advance as opposed to a time delay when he passes through it, and then manages to come out here on the right. And if this negative energy pulse is arranged so that the tidal forces are small, then Romeo would not feel particularly bad doing this. So, I mean, he has to take a leap of faith here when he falls into the black hole that this whole procedure will work, but he will not feel bad in any of no part of the process. So here, the interesting thing is how this wormhole picture gives a different perspective for how teleportation happens. So the qubit in teleportation seems to magically go from one place to the other. Here, it's going through this wormhole. Okay, and this is basically this whole evolution is similar to what was happening before in ordinary teleportation. So we have this wormhole is the entangled state. The fact that you have to send this early and then wait for a little while is the time evolution, which is, well, here it's sending Romeo closer to the black hole horizon, and is somehow scrambling the degrees of freedom of Romeo with the black hole degrees of freedom. In the boundary, it looks like something messy and complicated. Here in the interior, it's just simple motion through empty space. Okay? Then we do the simple measurement, and here the time evolution sort of unscrambles back Romeo and comes out of from the, well, this outside looks like a black hole. You send a negative energy pulse, and out comes Romeo. So it looks quite strange from the right point of view. Okay, so I guess what's interesting is how the qubit is transferred from one side to the other. Okay, very good. So we saw very different versions of connections between quantum mechanics and geometry. We started by saying that quantum mechanics determines the large-scale structure of our universe, right? So this is not some very esoteric thing. This is something we use to describe our universe. And we said that certain strongly interacting quantum systems have concrete gravity duals. And we said that how near-horizon dynamics of black holes is related to the chaotic dynamics of systems, and systems that have black hole duals are maximally chaotic. And we also mentioned that the structure of space-time is intimately connected to the patterns of entanglement. And we showed how entanglement is related to wormholes, and that teleportation is related to traveling through wormholes. So there are many challenges for the future. So in terms of these dualities, there are various types of theories you can have, all of quantum theories, and all of possible spacetimes, and there are various relationships between them. And we basically know some little dots here. We don't know the whole web of relationships between the two. Now another question is whether gravity is just an emergent description at large n, so it's only an approximation, sort of like hydrodynamics is an approximation to the macroscopic dynamics of some system, or whether it is independently defined as a theory of quantum gravity, valid even for finite n or small n. And that's, again, a question which we don't know, because we don't know how to define completely the theory of quantum gravity. From string theory, we have some evidence that it's probably the second, but we don't know what the true answer is. Okay, thank you.
Thanks, Juan. Fantastic talk, as usual. Juan will be continuing, by the way, tomorrow morning and Thursday morning at 9:30.
Yeah, I should probably say a little bit what I'll discuss in the next two talks. So tomorrow I'll give a review of SYK and ADS2. So the SYK model is a simple quantum mechanical model that has features similar to black holes, to near extremal black holes, and discuss the relationship between the two. And then in the next lecture, I'll discuss some more recent work in trying to understand traversable wormholes and well, even solutions for traversable wormholes in 4 dimensions.
So we'll take some questions, if that's okay.
Some of these wormholes that you described are very interesting for science, but not practical if you actually wanted to use them for traveling across space efficiently. Do you think a useful traversable wormhole of that type can be built, or is it precluded by chronology protection, etc.? Or can it be?
Well, so all the wormholes that you can build, it takes you longer to go through the wormhole than it takes you going through the ambient space, right? So it's not useful for the standard science fiction story. So you have to have a different science fiction story, like you are trapped inside a prison and they don't allow you to go, and then you create a black hole and you manage to escape. So if you want to make a story, you have to make a story like that. Now, what it will be useful for, I have no idea. So, but well, I can tell you that the reason we are studying wormholes is that I think they're useful for understanding the nature of space-time, how space-time emerges, and so on. So we are trying to learn lessons for how to build space-time by thinking about these weird objects like wormholes, because in this situation, space-time is built in a very strange way. And by looking at the strange cases, you might get true lessons. It's like, biologists study very strange illnesses or animals or whatever that to try to figure out general rules. Yeah.
What is this classical communication that you mentioned between Romeo and Juliet?
Yes.
This I didn't quite understand.
Well, so in standard teleportation, you can send a qubit by sending only classical information. That's the interesting aspect of teleportation. So let me just say a few more words. So if you have a qubit, right? A qubit is you have to say, well, you can say it's a spin that is in some direction, right? And in order to specify the direction, it looks like you need to specify many numbers, an infinite number of numbers, right? If you want to send it with complete precision. But if you're sharing an entangled spin already, and you want to, someone gives you a new spin and you want to send it, one thing you can do is to do this combined measurement, and then you can send that information about the spin by sending just two classical bits. So 0 or 1 and 0 or 1. So by sending those two classical bits, you can send the exact position of that qubit. So that's the magic of teleportation.
Hello. Just to sort of follow up a bit on a similar line. So you say you contrasted these two processes, one in the gravity and then one in the just in terms of the teleportation. Did you mean to say that in some regime they are actually dual?
Yeah. So they are, yes. Yeah, always whenever we are talking about gravity and the relationship to some dual quantum system, that only applies to very strongly coupled systems. So those gravity cases, those gravity pictures and so on, only apply for very strongly coupled systems. But they might apply in general, but not for standard Einstein gravity. There might be a version of quantum gravity that applies for even weakly coupled systems. Well, there is a version of gravity that applies for weakly coupled system, which is called Vasiliev gravity. But even for small n systems, let's say for just 2 qubits, is there a gravity picture? We don't know. We don't have a theory of gravity that is good enough. I mean, it's related to question number 2 there, that would apply even for an arbitrary system. But if we had such very general theory of gravity, then the idea is that those pictures would hold in all cases. So that's this idea of that ER is equal to EPR, that Einstein-Rosen bridges, which are these wormholes, and entanglement are related. They are the same. But we don't have a formulation of quantum gravity where this is true. So.
Thank you. So you have repeatedly emphasized that even in your paper with Stanford and Yang, that when Alice or Bob send a message from one side of the CFT to the other side, the message sails through a smooth geometry, and it feels nothing special. So does that hold true even if, let's say, the AMPS proposal were true? And if that were true, what would be the modifications, or what would the message feel?
Well, I think so. Yeah, the question was about the AMPS proposal. So AMPS stands for some initials: Almeri, Marov, Polshinsky, and Sully. And they found a particular version of the information paradox, the black hole information paradox. And they proposed that the resolution was that a typical black hole does not have an interior. It has a kind of firewall. And so you die not at the singularity, but when you cross the horizon. Now, they say that that's true for typical black holes, but I think in some of their papers they also say that if you have the thermofield double, then you wouldn't have these firewalls, and so the firewall, whatever it is, maybe it has to have the magic property of disappearing. Yes.
More questions? I was also wondering about one thing, since I know you have thought about this, about entanglement in an expanding universe, since you mentioned right at the beginning about the quantum mechanics at the very largest distance scale. So, So what is your thinking on that?
I don't have anything useful to say, but yeah, I mean, in the same way. So in well, in ordinary ADS CFT, we think that the entanglement patterns of the state on the boundary are represented by the geometry of the interior, right? So I guess in cosmology, the idea is that perhaps there is some description of the universe at late times, and then the correlations present in that late state well, can be represented by the previous time evolution. I mean, certainly in the ordinary time evolution, those correlations are created by the evolution, by the actual time evolution from the beginning of the universe till today. But you might think that maybe it's the inverse, that somehow there is some other principle that determines the state of the universe, and that the time evolution is a kind of illusion going back, and that once you have that state in the far future, you will resolve the Big Bang. It's simply you'll have some different description. But this is pure speculation. I have no idea.
Yeah, I have a question regarding these 2 points. Your original correspondence was the duality, actually, between a quantum field theory in 4 dimensions and a string theory in 10 dimensions.
Yes, yes.
So is it a duality, or you are just presenting a picture of kind of emergence of gravity? I think it's the exact duality between the two.
That's right, that's right. Yeah. So if we can define independently string theory, non-perturbatively and so on, then it would be, the answer to the second question is yes, and it would be an honest duality. Let me clarify a little bit.
Yeah.
So the definition we have of string theory is a perturbative definition. So we can talk first about free strings, then interactions. We can describe then interacting strings and so on. And in this context, it's in a 1/n approximation. So we have a 1/n expansion, and that's the definition we have of the theory. And so we can certainly one can check this 1/n expansion. So for example, for the free string, several people used sophisticated techniques of integrability to show that you get the same answer in string theory and in the gauge theory, in one particular example. So there you can check that precisely, and probably in the future this will be checked for all orders in the 1/n expansion. But the question is, well, is that enough to define the theory or not? I mean, I think typical string theorists think that the string theory is completely well defined, but even though we don't know the precise definition.
I think I feel that your duality idea looks more complete. Both sides should be complete, and it's just a dual relationship between the two theories.
Well, I agree. I think I prefer that possibility. But the number one is also a popular view among people who think about these things. So I should present both.
Thank you.
Okay. Any more questions? So if not, please come for the following lectures tomorrow and after. And if you are lucky, there is, I think, probably a high tea outside. So I invite you to come.